Cool. So this first one, I don't remember. This is definitely a U sub over here. But this is just a little trick I like to do. You've seen this. When you got an x squared in there, you got to bring that 2 down to the front. You can actually take it all the way out. So it's integral ln x over x dx. If you have any questions, just holler at me here. But that's how that's going to look. And that's a U substitution, right? So U is going to be ln. I told you that. Anytime you see a ln, it's going to be U. du is 1 over x, and you see that sitting right there. So this becomes 2 times the integral of U du. Just got to remember to change the limits. It's not from 1 to 4 anymore. If x is 1, U is ln of 1, which is 0. And if x is 4, U is ln of 4, which is ln of 4. So this just becomes 2 times U squared over 2 from 0 to ln 4, which becomes, if you plug in ln of 4, ln of 4 squared minus 0. So that's the answer to that one. Okay. Number 2, find the area. That's exactly what the integral does. It finds the area between a function and the x-axis, but we need to know what that graph looks like. So sine of x does this super cool little curve. Cool. This is pi over 2 right here. So pi over 6 would be somewhere like right here. Okay. This is pi. So 7 pi over 4 is like right here. It's in the 4th quadrant. So I'm asking you, what is this area here? Now, if you just integrate sine from pi over 6 to 7 pi over 4, you'll get an answer, but it's not going to be the right answer because I'm asking you for the area specifically, not the signed area, okay, not the actual integral. So this area here is going to be a negative number. So I got to make sure that I find that and make it positive because I want what the area is. So I need to integrate to pi first because that's where sine changes sign. Okay, and I'm only doing this because I asked you specifically find me the area. Okay, so we're going to go from pi over 6 to pi, and that's going to find the area in this little checkered pattern there, right? Okay. And then I need to find the integral from pi to 7 pi over 4 of sine of x dx too. Cool, but I don't want to add it, I want to subtract it because it's negative and I want to know what the actual area is. Okay, so the integral of sine, everybody knows, is negative cosine. That's from pi over 6 to pi. We'll do this first. So you get negative 1. When you plug in a pi there, you get negative 1. Minus, when you plug in a pi over 6, you get root 3 over 2. That's that first part. Cool. And then we have minus the integral of negative cosine from pi to 7 pi over 4. Cool. So it's minus, when you plug in 7 pi over 4, you're going to get root 2 over 2, but it's negative cosine, so you get negative root 2 over 2. Cool. And it should be minus, right, because it's always plugging pi, but it's negative cosine pi, which is negative negative 1, which is positive 1. Now we just got to simplify this thing. So this is really 1 plus root 3 over 2 plus root 2 over 2 plus 1. So it's really 2 plus root 3 over 2 plus root 2 over 2, which is a weird number, but that's just what it is. Okay? Now, again, if we had done the integral from pi over 6 to 7 pi over 4 the whole way, we wouldn't have got that. We would have got, like this back here would have canceled stuff out. We would have got negatives in there. It would have canceled. Okay, so that's that. And then the last one, this is something that we did very briefly last year. I also make sure you guys are familiar with this. This is called a differential equation. And you're going to be asked to solve differential equations. We're actually going to have a whole differential equation unit this semester. But what you need to do is separate out the x's and the y's because you got dy dx in there. That's what makes it a differential equation. And we need to separate out the x's and the y's. So the way you do that is, look, we have a dy over here. When you're adding in an exponent, you're really multiplying. So that numerator is really just that. So we'll leave this like that for right now. That's the same exact thing. Okay, but what that allows me to do is make it dy over e to the y is equal to e to the root x over root x dx. Again, any questions, Turn your mic on and say, yo, what's up? Okay. And then last thing before we're going to integrate both sides here, okay? But you don't want to integrate with an exponential thing down the bottom like that. That's weird. You want to rewrite it as e to the negative y dy. And this is okay to leave over here. This is going to be a u sub. And then we're going to integrate both sides. That's how you solve a differential equations, okay? That's called separation of variables. Now, diffeq in general, if you take the class, has all kinds of stuff in it. This would be like the first thing you guys do. But the integral of e to the negative y is e to the negative y with a negative out front. And that's the chain rule happening there backwards. We have to divide by a negative 1, technically. This integral over here, though, we would technically do, I'll do it over here just so we got some room. We would technically let u equal root x, because that's the exponent of e. That's how we handle exponential functions. If you got like a weird variable up there, you're going to let that be u. Then du would be 1 over 2 root x dx. But that means we need a 2 down there, so we put a 2 right here. That means we got to put a 2 out front. So that integral is going to become 2 times the integral of e to the u du. Right? Right. So that will become negative e to the negative y equals 2 e to the u, if you integrate that. But that's just root x, and there's a plus c over here. Just put a plus c on the x side. And that technically is a solution, but a lot of times they're going to want us to solve for y. Okay, so the solution to a differential equation is a y equals. So you want to know what y is that makes that true. Okay. Now, if they give us a point, we got to find plus c, but I didn't give you a point. I just said solve this. So plus c is just going to hang out there, and we got to get y by itself. So it's going to become e to the negative y equals negative 2 e to the root x minus c. You could technically leave it as plus c still because it's just some number. It doesn't matter if you're adding or subtracting. Now we got to get y down, so we're going to natural log both sides. So that becomes negative y equals the ln of this. Then we're going to divide by negative 1. So the answer to that differential equation is really y equals negative natural log of negative 2 e to the root x minus c. Okay, questions on that? How are we feeling? All right. We are going to talk about a lot of stuff today here, but the first thing is going to be area. So we just looked at the second question up there was find the area between sine and the x-axis. I'm going to ask this question here. Find the area between x squared and root x. Okay, I'll make this as simple as I possibly can. So if they ask you for the area between curves, what they're really saying is you got to find the area of a closed shape. Okay, like they're not giving me any bounds. So we need to know what this graph looks like. But you know that x squared looks like this, right? And root x looks like that. So the shape they enclose is right here. So I'm asking you to find the area of that shape. Okay, and the way we find area between two curves is we're going to use integrals, but I want to really hit hard like what's happening here. Okay, when we do an integral, so when we integrate a function like sine of x dx, let's make it even easier. Let's just do x squared for right now, from 0 to 3. Okay, graphically, what is happening there? So here's what we're looking at. There's x squared, and from 0 to 3. So you know from last year that we're finding the area in there. But what we're really doing, what's really happening, and if you understand this, is going to make the rest of the stuff a lot easier, is we're putting all of these little tiny rectangles in here, like this. We're filling this thing up with rectangles. Now, the rectangles are infinitely thin. I can't draw them infinitely thin, so I'm drawing them semi-thin. Cool? Like that. But if you look at each individual rectangle, okay, I want to know the area of each one. Well, the area of a rectangle is just the height times the base, right? Base times height, length times width, however you want to think about it. I'm writing like that on purpose, though. So the height of every single one of these rectangles is changing, but they're changing based on the same exact rule. Every single one of those rectangles, the top of it, the height of it, is on the function. So the top is just x squared. So the height of every single one of those rectangles is x squared. The width of every single one, and then the base of them is this infinitely small, thin sliver. Well, that's me crushing down the change in x, which is called dx. Okay, we're making an infinitely small change in x. That's what dx represents. So the area of one of those rectangles is x squared times dx. Now, because dx is infinitely small, right, that area of one rectangle is essentially 0. However, if you stack them all together and add them all up, you get the area of that shape. So again, imagine a bunch of infinitely thin rectangles in here. Right, so I mean, it would fill the whole shape. There's infinitely many of them. Is there 100,000 of them? No, there's infinitely many. Is there a million? No, there's infinitely many. Think of the biggest number you can think of. There's more rectangles in here than that. There are infinitely many rectangles in here. Cool. I need to add them all up. And you're like, well, how do I add up an infinite thing? That's what the integral does. It stands for S, right? Sum. We're summing them up. Okay, so we're adding up all these rectangles that are x squared times dx. And all the integral needs to know is, well, where does x start and where does x stop? Well, I'm going to let my rectangle start when x is 0, and I'm going to end when x is 9, or 3, I mean. Cool. And because we know the integral, the area under this curve is the same thing as the change in the antiderivative. That's how we actually calculate this if we're not using a calculator or something. We find the antiderivative, so we underive it, and we find how much it changes. That's why the area is what it is. If you put a 3 into there, you're going to get 9. If you put a 0 in, you get a 0. So the area in there is 9. Okay, you can really see this working. So the best, let me show you this too. So let's say we had to find the area. I'll just show you an example that this works, okay? Under y equals x from 0 to 4. So we know that area. Well, this is easy because that's just a triangle. Like I can find the area of that triangle in there. It's a half. Whoa there. You don't need calculus for this. It's a half the base times the height. Since this is y equals x, this is a 4 right there too. So that's going to be 8. The area that has to be 8. But if we think about it calc-wise, right, if we think about infinitely many rectangles in here, every single rectangle has a height of that function, which is x, and every rectangle has a thickness of dx, and I want to add them up from 0 to 4. And if you do that, you're going to get 8. It's going to work out. You get a half x squared from 0 to 4. Plug in a 4, you get 8. Plug in 0, you get 0, you get 8. Okay, and that's just an example of me showing you that, hey, this works. Cool? So that's what the integral is really doing. Now, we exploit the integral in several ways to make it do what we want it to do. So if I want to find the area in there, check this out. What we're really going to do is the same exact stupid thing. I'm going to put infinitely many rectangles in here. And that's going to find the area in between these curves. But now, so check it out. Every single one of those rectangles, again, is an infinitely small change in x here, right? Like we got like that base of each one of those is like a very, very, very small change in x. So that's dx, the base of every single one of them. Now the height, though, is different. The height's changing. So like you can see here, like the rectangle over here will be smaller than the rectangle in the middle, right? But no matter where I draw it, no matter where I draw them, the top of every single rectangle is root x, and the bottom of every single rectangle is x squared. So think about a number line here, right? Think about a thermometer. If let me come over here. If we had a thermometer, there it is, look at that thermometer, okay? And the temperature was up here at 90 degrees, but at nighttime it's down here at 82 degrees. If I asked you, hey, how much did the temperature change? You're going to tell me 8 degrees, because we're doing 90 minus 82, right? If I told you the temperature was, for some reason, root x degrees, and now it's x squared degrees, and I said, how much did it change? You're going to tell me root x minus x squared, right? That's just how much it changed. It went down that far. So it's root x, take away x squared. That's what's in here. Cool? So that's what the height of my rectangles is in here. It's root x minus x squared. And no matter how you do this, the area between curves will always be the top minus the bottom. That's how we subtract on a number line, top minus bottom. So that's root x minus x squared. That right there represents the area of every one of those rectangles dependent upon the x value. And I want to add them up from when they start, which is 0, to where they end, which is where these two curves intersect. And they happen to intersect at 1. So if I integrate that, that's going to tell me the area between those two shapes. Okay, this is also, by the way, the exact same thing as doing the area under root x So think about the area under root x. That would look like this from 0 to 1. We'd get this area here, right? That's what that would do. And subtracting off the area under x squared. That's going to leave me with what I want. Cool. So if I take that and I subtract off the area down here, that's gone. What I'm left with is the area between them. So those are both the same exact thing. But in general, we're doing top minus bottom. Cool. If questions, everybody feeling good on this? I'm going a little slow. I hope I'm going a little slow to make sure this makes sense. Yes, we would have to do this integral, but for right now, guys, I'm going to say most of the time, just set up the integral that will find the area. All right, and that's what it is. We could do that by hand if we had to, but we could also do it with a calculator or online. I'm not too concerned about that right now. It's the setup. So that's an example of where they don't give you any bounds. So if they give you two functions and they don't give you any bounds, or sometimes 3 or 4 functions, you just got to sketch them out and see what shape they enclose. Okay. If they give you bounds, like this one right here, find the area between x squared and x cubed on 0 to 4. That 0 is not red for any real reason. It just is red. I don't know why. So now I'm not asking for the area between the two curves. If they enclose it, I'm telling you I want to go from 0 to 4. So we still need a graph of this. So you know that x squared looks like this, and x cubed is going to look like, they're going to hit it 1, 1 again, right? Yeah, x cubed, I'm going to exaggerate this, comes in underneath of it and then crosses it. Okay, let me draw that with a different color. So here, yeah, x cubed is going to look like this. Okay, and x squared is going to look like this. It's going to come in like that, and then it's going to be on top of it for a little bit, and then they cross it 1, 1. Okay, so they do enclose a shape, right? But I'm not asking you to find that area. I'm asking you to find the area from 0 to 4. So from 0 to 4, let me just draw that shape. From 0 to 4, we have the parabola. Again, I'm going to exaggerate this really, really badly here. We have the parabola coming in like this, and then we have the cubic coming in underneath of it and then crossing it. So let me switch to blue. So the cubic comes in like this and then crosses it, something like that. So we want the area. You can see it happening right there. We want the area. Let me switch colors again, just because I can. Look at all the colors I have. We want the area in here and in here. Now, I chose this question for a reason here. What happens is the top and the bottom change there, right? In my first section, the bottom is x cubed and the top is x squared. So rectangles in that section are defined by their height, which is x squared minus x cubed, times their thickness, which is dx.
Are 3's cubed?
Get out of here, yes. Okay, go away, I'm working. In the next section, though, x cubed is on top. That doesn't sound very nice. I'm very nice to my children. And x squared is on the bottom. So those rectangles are defined by, here you. Stop. Hey, get out of here. I'm serious. I'm working. Okay, I love you. We'll play later. So x cubed minus x squared. Okay, because they're defined differently, we have to do 2 different integrals. So to find the area in here, remember, this is the point 1, 1. To find the area that I asked you to find, which is here and then here, I need to do rectangles that are x squared minus x cubed times their thickness, which is dx. And we're going to go from 0 to 1. That's that first section. Plus, hey there, Chief. Plus integral from 1 to 4. Now I'm going to 4 because that was what I said we had to do originally. We got to go from 0 to 4. But the rectangles from 1 to 4 are defined by x cubed minus x squared dx. And that's how you're going to find that area. So let me stop real quick. How are we feeling? Questions? Your homework over the weekend is to find the area between curves. I put the answer key online, and I put the homework assignment online already too. Okay? And while I'm thinking about it, what's up?
Is that in addition to all the stuff you assigned yesterday?
No, the area homework was online yesterday too.
Oh, okay. All right.
So what I want you to turn in, and I don't know if I even created an assignment for this yet, so let me double check. So I definitely want you to turn in the area homework, okay? And I want to talk about how we're going to submit stuff, and then I'm going to go a little further with some math things. So, hey, Elliot, how's that chrysalis looking? Hasn't come out yet? We have a butterfly that's about to come out of its chrysalis. Okay. Oh, when it comes out, it's going to be big. So either way, I'm going to make an assignment if I haven't yet. It's going super slow here. For you to submit the area homework, okay? And then you also got the Delta Math stuff, which will be submitted automatically. Come on. So, all right. So I made this welcome package because I want you to submit that. I don't know if you guys have yet. I want to go over how to submit things again real quick, though, okay? So you have to submit it in PDF format, just like last year, right? I don't want a bunch of picture files emailed to me. So the only way you can submit something is to go to the assignment, open it up, and upload your PDF. So before you do that, you got to take pictures of your work, put them in order in a Word document or a Google Doc, I don't care which, okay, and then save it as a PDF. On the Google Docs, you have to download it as a PDF. But either way, it'll save, and that's what I want you to upload, okay? And in terms of downloading things that I'm putting online for you, let's go to modules here. You can just download the day of what you need. It'll never be more than like 3 things. Usually it'll be like 1 or 2, okay? But if we go down to, here we go, the week of the 14th, if you go into synchronous work, okay, so all I've set up so far is Monday, by the way. But over the weekend, I'll have the rest of the week set up. And throughout the week, I'll add videos to things too, so you guys can go back and check stuff out if I don't do it ahead of time. But you need to download on Monday. There you go. There you go. Rotations practice. Okay, so that's what we're going to do in class, and you're going to finish that for homework.
Just letting you know, we're not seeing Canvas. We're still seeing the paper.
Oh, I forgot. I put it. God darn it. Thank you. Please tell me that earlier, guys. Okay. Anyway, it's in Canvas. Just download that stuff for Monday before class. That's all. Cool. But let me go back to here. Is everybody clear on submitting their work as a PDF, pictures in order, name at the top? Okay. Elliot, cut it out, dude. Okay. So go ahead and do this next question for me then. I'm going to give you a few minutes, okay? Find the area between those 2 functions. So graph them out first, and I'll graph them on my screen too, just so we're all together. You have x squared goes like this, root x goes like this. Let me make this more exaggerated so it's a little easier. So this is 4, and they intersect at 1. So just write the integral that's going to find that area. You don't have to evaluate it. Go on this or something. You have to relax. You can't be running around with Luke.
Well, Luke said it's okay.
So you're done. Luke, are you doing small groups right now? No. No, you just have small groups, and he has break time to do Lexi and stuff. Elliot, come here. Okay.
I'm doing it next to you.
You gonna do it for 15 minutes?
Yeah.
Okay, go ahead and get that done. So I'm hoping you're telling me the first rectangles from 0 to 1, because the top and the bottom change there, are root x minus x squared dx, plus the area from 1 to 4 of x minus root x dx. How we doing? Everybody good? Okay, so I want you, what we're really doing there, again, just to highlight this, like let's just look at this first section, is I'm really subtracting the y values, right? y2 on top minus y1 on the bottom, but I'm using x to do it. I'm using my x to determine what the y value is. For instance, at 3, which would be like right here, the top of it is 9 and the bottom of it is root 3. So the height of that rectangle is 9 minus root 3. Cool, but that's only at 3. Everywhere, though, it's the x squared value minus the root x value in that section. Okay, now let me show you something that you might not like. So I got to go off script here. So if you downloaded this, just add this in somewhere. Let's say we had, let me see here. I'm going to say e to the x, which looks like that, and x plus 2, we'll say. Cool. I want to find the area in there. Well, you can see that x plus 2, no matter where you draw these rectangles, the top will always be x plus 2. So again, I'm saying we have e to the x and we have x plus 2. So the height of every one of those rectangles is this. And we would integrate that. So now I don't know where those curves intersect. We'd have to use a calculator. But let's call that value there a, and this value here b. So I'd have to integrate from a to b. Matter of fact, let's just go ahead and find those real quick so I can show you something. I hope that makes sense. I hope that's pretty simple. Again, any questions on where that's coming from, let me know. But come on, calculator. How could this be so slow? Okay, you know what? Let's just use stupid Desmo. Maybe that'll be quicker for me anyway. Okay. Ooh, maybe not. Maybe the internet's not free. Come on, baby. You can do it. My internet's working so hard right now. There we go. Look at that. Doesn't make you happy seeing a blank like grid. There we go. Okay. So
We can't see it. We're still seeing the worksheet again.
oh my gosh. Thank you. Is anybody else here? How come no one else is talking to me? Okay. Yeah, stop presenting. Oh, Lord. Hello? Stop presenting. Okay, whatever. Just look at OneNote then. It doesn't matter. I'm telling you, the intersection here is negative 1.841. So this is negative 1.841. But the y value there is what I really want to know too, is 0.159. Cool, comma, 0.159. So that's that point there. And the other point is 1.146. So that's this point right here. 1.146, comma, 1.146 and 3.146. Oh, because it's plus 2, that makes sense. 3.146. Okay, now, here's why I'm telling you that. If we do, why did I just erase that? What am I doing? I have to add some RAM to this computer. Maybe that's the problem. There we go. Okay. So if we integrate, I want to delete this. If we integrate this from our x values, right? So negative 1.841 to 1.146. Does everybody see that right there? That's going to find the area in there. Okay? But that's me drawing my rectangles vertically. So the whole point of this entire presentation, y'all see my screen still, right?
Yep.
Thank you.
Yes.
So let's look at that same exact shape, which is this line and like this. Sometimes it makes sense, not in this particular case, but sometimes it makes sense to define our rectangles horizontally instead of vertically, right? We can imagine them all horizontally, like this. Cool. That would still spread that entire area, right? It would fill the whole area and find it. So those rectangles have a height that's not this. Now it's dy. Now I'm crushing down the y value really, really tiny. Okay. Now it's dy, but their base is going to be the width of every one of these, and that's changing. So think about this again on a number line. Okay. If you think about this on a number line, if I said, hey, here's 2 and here's 8, if I said how far apart are those numbers, you would do 8 minus 2. You would say, hey, they're 6 apart. Cool. And if this side happened to be a y squared and this was like 2y, I'm just making these up. Now the distance between those is y squared minus 2y, just whatever those numbers happen to be. Okay. Let me see here. I'm using y for a reason. Cool. Because my rectangles have a height of dy, that's what's going to be the end of my integral right now. Okay. Which means just like when I was using dx's, my height had to be in terms of x. If I use dy, which is horizontal rectangles, my width has to be in terms of y. So this over here was the curve y equals x plus 2, right? That was a line. But what I would need to do is solve that for x. Those are the same curves, right? Y equals x plus 2 and x equals y minus 2. They're the same thing. So this is the left side of every single one of those rectangles. And on the right side, it should be e to the x. But if I solve that for x, I get x equals ln y. So the width of those rectangles is ln of y minus 2. That's going to find the same exact area. But now I need to add up all of those rectangles. And now I need to tell it what y is doing, not x. So x was going from negative 1.841 to 1.4 or 146. And again, all I was doing was putting rectangles like this up and down from where they intersect to where they stop. What I need to do down here with y's is put rectangles like this where they start all the way to where they stop. So that's going to be from 0.159 to 3.146. And the whole reason I was showing you this is I found those values because I want to show you the same exact answer. And while that might not blow your mind at all, what that does is it gives us two integrals that have the exact same value. And a lot of times in math, that's a pretty powerful thing because sometimes one way to integrate is super difficult and the other way is easier. It came out. Hang on, guys. Come with me. Going off topic here. All right. So. Oh! How do I turn this off?
The butterfly is out.
Okay, hang on. Oh, it's not working. All right, guys, my internet's going super slow, but we just had a butterfly get born out of our chrysalis. Luke, mute yourself. This isn't working.
That's awesome.
It was in a chrysalis for like 2 weeks. It just came out. So I can't. Oh, now my camera's going to work. Great. Well,
Does it have a name?
Yeah, it's calculus. Butterfly. No, I don't. So, well, we can't keep it for long. We let it go today because they only live for a little bit. I don't know if you guys know this. Monarch butterflies like fly up from Mexico, right? But they do it in 5 stages, like 5 generations. So let me see here. They're down there in the winter, like, so they fly back down for the winter, right? And then they kind of just chill until the springtime, and then they have babies. And those babies come out and they fly a little bit north, and they have babies, and then they die. And this, so then like the grandchildren of the first group, right, are now born. They fly a little more north, and then they have babies and they die. And then they fly a little more north, and they have babies and they die. And then they fly a little more north. So they do that 5 times. Okay. And on the 5th generation, those bad boys and girls come out bigger than the rest, and they fly all the way back to Mexico to start the process again, which is crazy. Just a little tiny butterfly. Anyway, that's what I learned this summer. So let's go back to actual math, though. Oh, we're going to be out of time. Well, that's okay. Let me show you real quick before you get out of here. Just that these are going to be the same exact answer, okay? But notice, look, the first one, by the way, is oh, I got to share my calculator with you. God. But the first one, we can integrate, right? I know how to integrate e to the x. But the second one, the y version of it, has an ln of y in it. And we don't know how to integrate just ln of y. Cool. So the x version of this is easier. And that's not always the case. Sometimes the y version is easier. And a lot of times you can do both of them. It doesn't really matter. So if you were to put both those into a calculator, and again, this is going super slow. I'm trying to present my whole screen. Come on. Stop presenting. Is that going to work? Okay. I stopped presenting. Let me present my whole screen now. Is my audio choppy at all? Like, I feel like the video was super choppy.
No, your audio is fine.
Good. Okay. So now you see my whole screen. There we go.
No, not yet.
Yeah, we can't.
Still, it says I'm presenting.
Oh, there we go.
All right.
Wait.
So, hey,
Yeah, there you go.
Elliot, headphones in. No, they're not. Dude, I'm telling you, I can hear your audio. Plug them in further. Hang on. Dude, this gives you a problem. Plug this in. Okay? That pink thing keeps coming out. There. Okay. If we do math 9, right? We're going to integrate from, I'm just going to type these in, -1 point. You guys get the point of what's happening here already, but 0.841 to 1.146 of x plus 2 minus second e to the, oh, not f's, oh, go back. Oh, this is so cumbersome with all this stuff on here. Okay. How about that football game last night? Pretty good, right? Oh, yeah. So x, where am I right now? X. There we go. Oh my gosh. Boom. The area in there is 1.949. Cool. But if I do it with a y, so one fairly important thing here, math 9, is even though there's y's in this second integral down here, we're not going to put y in there. We're going to use x's on the calculator. The calculator doesn't care what variable you're using. I get asked every year, how do I put y into my integral? You don't. Don't worry about that. Just put x's. It's just a placeholder. Cool. So we're going to do ln y, or ln x, minus, now in parentheses, the bottom. I'm subtracting off the bottom, or the left side, I guess, right minus left. But I got to put it in parentheses. If you don't put parentheses here, it's not going to do the right thing. You got to subtract off the quantity. And I'm using x's, so dx, but really on my paper it's all y's. And please be the same number. Boom, there you go. Okay, a little bit different because we rounded, but there you go. So we can find area 2 different ways. Whew. So on your homework, you can do whichever. Most of the time it's going to be x's. Okay, but every now and then you'll see one that's better for y, or they'll define a curve in terms of y initially. All right, any questions? How are we feeling? Excellent. So let me stop this.